All right, in this section 10-7, we're going to be talking about graphing polar equations. Now, because of the circular nature of the polar graph, okay, the graphs are going to look tremendously different on a polar coordinate system than they would on a regular rectangular coordinate system. And that's what we're going to be focusing on this section. They're basically the different types of graphs are grouped into several different groups based on what the equation is, because the form of the equation would dictate the type of shape that's formed on a polar graph. And so, for example, if we have an equation of this form, r equals a cosine theta or r equals a sine theta in this form, it's going to produce a circle. Okay, and the location of the circle being determined upon whether you have cosine or sine, and then the size of the circle would be determined by the value of the a. So, like for example, if you have cosine with the value of a is greater than 0, so that a is positive, then the circle would be oriented this way. If it's negative, then the circle flips and orients this way. And if you change it to sine with the a greater than 0, the circle is up above the pole right here. And if you change it to negative, it sits down here. And like I say, the size of the circle depends on the value of a. All right, the next group are called limaçons, is the proper pronunciation, right? And these equations have the form r equals a plus or minus b cosine theta, or a plus or minus b sine of theta, right? And the a and the b for these graphs both have to be positive. And so we can see kind of the shape of each limaçon based on the characteristics of the equation. So if you want a limaçon with an inner loop, then the a has to be greater than b, and the equation would be a minus b sine of theta. That would produce a limaçon with an inner loop. Okay. If you want to produce a limaçoid that is classified as a cardioid, then a could be equal to b, and then the sign in between the terms is plus, and this function is cosine, then that would produce this type of limaçon. If you want a dimpled limaçon, then a has to be between b and 2b. The function is cosine separated by a minus. And a convex limaçon, a has to be greater than 2b, the sign between plus and the function sine. So just by changing signs and values of a and b and sine to cosine, vice versa, you will get different types of limaçons. Okay? The next group of graphs that are produced are called roses, right? And roses kind of have the form r equals a cosine in theta or r equals a sine in theta, where the n has to be greater than or equal to 2, and it's an integer, and the rose has n petals if n is odd, and 2 n petals if n is even. All right, so the amount of petals in the rose is determined by the value for n. All right. So like right here, for example, if n is 2, all right, so that's even. So it has 2 times n petals. It would have 4 petals, right? And so here, if my n is 3, 3 is odd, so it would have 3 petals, and so forth, right? 4, double that to 8 petals. 5 would have 5 petals, and so on. All right, so that's kind of how that works. And again, this would be the form for the equation for the roses, all right? Let's see, what else? Then a couple more groups of graphs. Lemniscates, right, is the next set, and it's kind of like a looped graph, almost looks like an infinity symbol. And those have the form r squared equals a squared cosine 2 theta, or r squared equals a squared sine 2 theta. And if it's cosine, then it has this kind of horizontal orientation to the graph. And if it's sine, it almost has what we would call a diagonal orientation to the graph. And of course, the value of a would determine on how big the graph is, the loops are, in other words. Then the last one, you've got a spiral, right? A spiral of Archimedes, which has this form, R equals A theta plus B. And so if you've got your theta that's greater than 0, then you've got a spiral that comes off and appears this way, so it shoots out here and then starts going around, so it really kind of shoots out from the top of the pole. And if the theta is less than 0, then it actually shoots out from the bottom of the pole. And like also, as in the previous ones, the value of A determines kind of the shape of the spiral, like how tightly wound or how widely it loops out. All right? So, like, what are we going to do with this? Really, all we're going to do is we're going to look at equations and try to identify what the graph would look like, or try to be able to identify which graph matches an equation is really all that we're going to be able to do with these, right? So we're not going to do a whole lot with the different types of equations and plot points and try to find the equation of a spiral or that sort of thing. It's really merely just going to be, all right, so which equation matches this graph and what type of graph is it? Is it a circle, a limacone, a rose, a lemniscate, or a spiral? All right. So, for example, okay, we can take a look at an example like this. It says, identify the type of curve given by the equation, then use the symmetry, zeros, maximum, R values to graph the function. All right, so the graph is really already given to us, but if we wanted to graph it, we do have a couple of different ways. By hand, it would look like this. We could plug in values of angle values, use the equation to get radius values, and then actually plot the points until we can see what shape is going to be formed here, right? However, that is the long, non-technology-based, laborious way to do it, all right? So we have calculators that we can use for these things nowadays, and so your Desmos calculator can graph, has the capability to graph in polar coordinates. All you have to do is go to the settings up here at the top, and you can just change your grid from rectangular to coordinates right here, to polar, all right here. Leave it in radians. Then once you've changed it to polar, you can just type the equation in, typically the way it is. However, if it's r squared, if we wanted to graph this on our Desmos calculator, it doesn't take it as r squared, but it will take it as r, which means all you have to do is take the square root of both sides. So I can write this as, we'll go ahead and get r from my ABC menu, r equals, and then I need to take the square root of this when I plug it in. So it would be square root of 16, get sine of 2, and then theta is on the ABC menu out here, right? And so, as you can see, it has graphed this for us exactly the way that it's graphed here when it was done by hand. All right, so you can use your Desmos calculator on your phone in order to see what the graphs of these equations look like. And of course, it asks us to identify it. So, what type of a graph is it? It's a lemniscate. And you can see, since we're using sine, then it's oriented diagonally, right? So if it was cosine, if I just were to change that to a cosine, let's see what would happen. I would take it out, and you see we've got a spiral. So let's see. So if I go over here and change this to cosine, you can see that it changes orientation to horizontal. And by the way, we can just go ahead and name it. That is a lemniscate, because it asks us to identify it. All right, so there you go. The next one, we're given the graph. If you wanted to do it by hand, you could plug in values, like they've done here, of the angle, which will provide a resulting radius, and then use angle and radius to get some points on here. And once you have enough points on here, you can see that this develops into a spiral. So we'll go ahead and identify it. Okay, so we have identified it, and let's graph it. So I'll come back here, and I'll leave my R on here, and we'll call it R equals 3, not pi, that's not what I wanted. I wanted 3 theta. Alright, so we can see our spiral here, and if I zoom out I can see more of it, right? And we notice that it is the same graph that is here. Now, just to kind of look at the form for the spiral, there can be a b added to the end of that. Let's see how that actually changes my graph. So if I go over here and, like, say, add 2 to it, alright? Let's add 15 to it and see what happens. Alright, so it just stretches out the, actually the starting point of the spiral then moves to 15, right? So if there's nothing there, then the spiral is actually starting at 0. And if I begin to add values, then it moves the starting point, okay, of, whoops, didn't mean to do that, starting point of the spiral out to that point on the axis. All right? And so, like I say, all we're really going to be doing is trying to identify it. And on your quiz, that's all it is. It gives you a graph, and then it gives you a set of equations to choose from, and your task is to match the polar graph to the polar equation. And that's it.